Hello everyone. Today's session we are going to discuss about relationship between power spectral density and autocorrelation relation. Okay. Myself, Dr. G. Karthik Reddy, working as Associate Professor in the Department of EC, MLR Institute of Technology, Hyderabad. In this session, we are going to discuss about the power spectral density, autocorrelation function, and the relationship between power spectral density and autocorrelation function. Okay, the relationship between power spectral density and autocorrelation function. Okay, here we are having the statements Rxx of tau is the Fourier transform pair of power spectral density. Okay, this is the first statement. Okay, all is same. Okay, the relationship between power spectral density and autocorrelation function or Rxx of tau. Next, time average of autocorrelation function, time average of autocorrelation function and power spectral density form a Fourier transform pair. Or we can also tell that state and prove the WK relation. The abbreviation of WK relation tells that, okay, these are the two scientist names, Wernier Kinchy relation. The Wernier-Kinchy is that these are the scientists who has identified the relationship between autocorrelation and power spectral density, which form a Fourier transform pair. Okay, they may ask in the exam related to any of these statements and calculate the proof related to these statements. Now we will discuss the proof related to the relationship between power spectral density and autocorrelation function. The statement tells that, okay, the time average of autocorrelation function form a power spectral density. Okay, you know that inverse Fourier transform. Okay, this is an inverse Fourier transform Rxx of tau or Rxx of t comma t plus tau, which is equal to Rxx of t comma t plus tau, which is equal to 1 by 2 pi integral minus infinity s xx of omega e power j omega tau d omega. This is an inverse Fourier transform of that, or s xx of omega is equal to integral minus infinity r xx of t comma t plus tau e power minus j omega tau. This is a Fourier transform and this is the inverse Fourier transform, because r xx of tau is Fourier transform to s xx of omega and is inverse Fourier transform to r xx of tau. Okay, these relations we have to prove it. Now next, this is inverse Fourier transform, this is a Fourier transform. Okay, these two formulas we are going to prove it. Okay, S xx of power spectral density. Okay, S represents the power spectral density, x represents, here we are considering let x of t is wide sense stationary random process. We are considering x of t is a wide sense stationary random process. Now next, A is the time average of autocorrelation t comma t plus tau into expectation of my e power minus j omega tau d omega. This is a formula of Fourier transform. Now next, you know the formula, one more definition of power spectral density. What is the definition? S xx of omega is equal to limit t tends to infinity expectation of mod xt of omega whole square by 2t. Okay, this is one more definition of what is that power spectral density. Okay, the mod xt of omega, you can write this as xt of omega into xt of omega conjugate. Okay, same thing, in place of mod xt of omega whole square, you can replace with xt of omega into xt star of omega. This represents conjugate of this. Okay, conjugate of this. Now next, xt of omega. We know the formula of xt of omega, which is equal to integral minus t to t x of t. Okay, you are considering t as t1 e power j omega t1 dt1. Now next, xt conjugate of omega, integral minus t to t x. Yet second time, consider this as conjugate as t2. Here if you apply this conjugate to here, then you are going to get negative sign, exponential to the power of e power minus j omega t2 t2. Okay, same thing they have represented here. Here what you are having, limit t tends to infinity 1 by 2t, expectation of those two terms. Okay, those two terms. Now what you have to do, you have to further simplify this. Expectation integral minus t to t, integral minus t to t x of t1 x of t2. You apply the e power j omega t1 minus t2 dt1 dt2. Okay, now when you apply the expectation to this term, okay, expectation is always applicable only for the random signals and random process. That is, expectation of this is called autocorrelation function. Okay, this is autocorrelation for the time instance of t1 comma t2. Okay, here limit t tends to infinity 1 by 2t integral minus t to t minus t to t 2 times, because for the two different time instance rxx of t1 comma t2 e power j omega t1 minus t2 dt1 dt2. Now next, what we had to do, now what we completed this portion. Now what we required, the portion, this part. Okay, this is the average power. Next 1 by 2 pi integral. Okay, this is a inverse Fourier transform. Okay, you have to substitute this part. You substitute this part in this equation. Okay, then what you are going to get, 1 by 2 pi integral minus infinity to infinity s xx of omega is what, limit t tends to infinity 1 by 2t integral minus t to t integral minus t to t rxx of t1 comma t2 into e power j omega t1 minus t2 dt1 into dt2. You substitute that relation. Okay, substitute that part. This is a portion we have substituted. Now next, e power j omega tau d omega. Now again rearrange the terms. Okay, e power j omega tau plus t1 minus t2. That part you will get here. Tau t1 minus t2 rxx of tau. Okay, you take this, rearrange the terms. You take this 1 by 2 pi integral minus infinity to infinity this portion. Okay, this portion you are having. Okay, integral minus this portion into this simplified form. You take this part. Now next here, whatever you are having, rxx of t1 t2. Okay, this is the limit t tends to infinity 1 by 2t integral minus t to t integral minus t to t rxx of t1 comma t2 1 by 2 pi integral minus infinity infinity e power j omega tau plus t1 minus t2 d omega dt1 dt2. Okay, we got up simplified, we got up to here. Now we have to further simplify this. Before further simplifying this portion is further simplified by using the property of impulse. Okay, by using the property of impulse. Okay, you are having the property of impulse based on the property of impulse. Okay, here in area under the impulse function of Fourier transform. Fourier transform of impulse signal is 1. Okay, x of t is equal to del of t. Okay, here integral minus infinity infinity del of t e power minus j omega t by 1. Okay, always the Fourier transform of the impulse signal is 1 by based on that relation. Okay, you take the 2 pi outside, 2 pi cross multiply it, then again you will get the same portion 1 by 2 pi e integral minus infinity infinity e power j omega t. This is the basic definition of impulse signal. Okay, basic definition of impulse signal 1 by 2 pi integral minus omega to omega e power j omega d omega. Okay, instead of e power j omega, we are having e power j omega tau plus t1 minus t2. Okay, same definition is same, just in place of tau t you are having tau plus t1 minus t2 you are having. Okay, just substitute, then what you are going to get, del. Okay, here for t, del of t, this is a e power j omega, del of tau plus whatever you are having t1 minus t2, this is a what you are going to get. Okay, 1 by 2 pi integral minus infinity infinity e power j omega tau plus t1 minus t2, okay, d omega. Then what you are going to get, this one, which is equal to del of tau plus t1 minus t2. Okay, del of t1 minus t2 is this one, the dt1 into dt2. Okay, now we got this one, we simplified, we got up to here. Now next, what else is left? This portion is completed, which is equal to del of, okay, del of whatever you are having tau plus t1 minus t2. Okay, we completed this portion. We completed this portion simplification. Okay, and we replace this one. Now next, so after finishing this, whatever we required remaining portion, we have to simplify it. Okay, now Rxx of t, in t is called t1, okay, t2 is called t1 plus tau, okay, t1 plus tau, then substitute it, then what you are going to get, t1 is equal to t, t2 equal to t, okay, here whatever you are having t plus tau, whatever you substitute it, then you will get Rxx of t comma t plus tau, remaining portion will be cancelled out. Then this is called, this is a formula of what? Time average of time, limit t tends to infinity 1 by 2t integral minus t to t Rxx of t comma t plus tau. This is a definition of time autocorrelation function. Time autocorrelation function. Okay, and this represents that a of, okay, a of Rxx of t comma t plus tau. Okay, now we got this relation, which is equal to LHS part you are having Sxx of omega. Means this form a Fourier transform pair. This statement tells that the time average of, okay, the time correlate, okay, time ergodic or time ergodic in correlation sense or in autocorrelation sense is a Fourier transform with respect to power spectral density. Or this one you can take in the Fourier transform pair, okay, Sxx of omega is equal to integral minus infinity the time ensemble, okay, time part, time average of autocorrelation function Rxx of t comma t plus tau e power minus j omega tau d omega. Now exactly this is in the form of Fourier transform. Then finally we can conclude that Rxx of tau and Sxx of omega form a Fourier transform pair. Okay, if you apply that, here you are not having any wide sense stationary. For wide sense stationary, what happens? Wide sense stationary, what is the condition? Two conditions you are having. Expectation of x of t must be constant and autocorrelation function must be function of tau and must be independent of time t. Then t2 minus t1, then we will get Rxx of tau. Now we can conclude that Rxx of tau autocorrelation function is a Fourier transform of power spectral density, and the formula is of Fourier transform pair, okay, Sxx of omega equal to integration minus infinity Rxx of tau e power minus j omega tau d omega. Or inverse Fourier transform Rxx of tau equal to 1 by 2 pi integral minus infinity Sxx of omega e power j omega tau d omega. Okay, in exam point of view, in the problems, numerical problems, they will give this as an input. They will give the autocorrelation function. They will ask you to calculate the power spectral density, or they will give the input as power spectral density they'll ask to calculate the autocorrelation function. Okay, one is either they may give either autocorrelation function or power spectral density, or either they may give the x of t, they'll give some random signal or some periodic signal. Then first you have to convert this into the form of autocorrelation function. After completing that, you have to substitute in this, then we have to calculate power spectral density. This is the easiest approach to calculate the power spectral density if they give x of t equal to some sort of signal notation. Okay, these are the relationship between power spectral density and autocorrelation function. This relation is also known as Wernier-Kinchy relation or WK relation. Okay, in this session we have discussed about the relationship between autocorrelation function and power spectral density form a Fourier transform pair. Thank you.